Hi everyone. Today we are going to start our third lesson in our probability unit, and we will be discussing conditional probability and the multiplication rule. Over the next couple days, we will be discussing a couple different objectives. Our first objective is to be able to determine conditional probabilities. Our second objective, to distinguish between independent and dependent events. This will be our focus today. Tomorrow, we will discuss the multiplication rule to find the probability of two events occurring in sequence, and also using the multiplication rule to find conditional probabilities. On this slide, we will begin to discuss conditional probability. Conditional probability is defined as the probability of an event occurring given that another event has already occurred. For example, I could say I'm going to flip a coin 2 times. I've already flipped the coin once and got a heads. What is the probability that on my next flip, I get a tails as my outcome? We should know the answer to this already, that on the second flip, we have a 1 out of 2 chance of getting a tails. Therefore, the events are independent. Because one outcome, the fact that I got a heads already did not impact whether I would get a heads or tails on the second flip. We will not talk about independent and dependent events right now, but we will on later slides. So to write in mathematical terms the probability of getting a tails given that I already got a heads, right, outlines this notation right here. The P stands for probability, B is event B, given is the vertical line, and A is event A. So in my example, we would have written the probability of tails given that we already had a heads. And the answer to that was 1/2. Because each flip is independent of previous flips, the probability of tails is just 1 out of 2. We'll look at additional examples. This example discusses a situation we can use cards, where we're using cards, 2 cards are selected in sequence from a standard deck. Last week we discussed that a standard deck of cards has 52 cards. A standard deck has 52 cards. Find the probability that the second card is a queen given that the first card is a king. Assume that the king was not replaced into the deck. So here's what we're going to write. We're going to say, what is the probability of getting a queen given the fact that we've already selected a king from the deck? Since we're not replacing the king after I've taken it from the deck, there's only 51 cards left in the deck. Of those 51 cards, how many of those are queens? Well, you should be thinking that there are 4 queens left in the deck. So our probability of pulling a queen from a standard deck of cards, given that we have already pulled a king from the deck and not replaced it, is 4 out of 51. Some additional examples with conditional probability often use a frequency table. Below, I've given you a frequency table that shows the results of a study in which researchers examined a child's IQ and the presence of specific gene in the child. Find the probability that a child has a high IQ given that the child has the gene. So looking at this example, we are only focused on the children that have the gene. Okay, so I'm going to go ahead and highlight those that have the gene. Gene is present. I'm highlighting this first column. That is the only population, that is only the group that we want to focus on, not the population, but only the people that have the gene present. I don't care about anyone that doesn't have the gene. It's saying that we've already determined that the gene is present, right? So how do I know that? Because it says given that the child has the gene. So I'm not focusing on any children that do not have the gene. So our probability looks like this. Find the probability that a child has a high IQ given that they have the gene. Okay, I didn't spell out the whole word gene because I ran out of room there on the side. But given the fact that they have the gene, find the probability that they have an high IQ. So there are 72 people total that have the gene present. And of those 72, 33 of them have a high IQ. So the probability that a child has a high IQ, given that they have the gene present, is 33 out of 72. Now we will begin discussing independent and dependent events. I discussed briefly that when we were flipping a coin that the events, each flip, the outcomes were independent of one another. An independent event is the occurrence of one of the events that does not affect the probability of the occurrence of the other event. For instance, the probability that I get a tails is not affected by the fact that I got a heads on the first flip. This is called independent events. The probability of getting a tails on the second flip is not affected by the fact that I got a heads on the first flip. So there's a mathematical formula to determine whether events are independent of one another. Here we have the probability of B given A is equal to probability of B, or the probability of A given B is equal to the probability of A. If the probability of B given A is not equal to the probability of B, right here, or the probability of A given B is not equal to the probability of A, then you can say the events are not independent and thus considered dependent events. Okay, so you want the probability of B given A equal to the probability of B, or the probability of A given B is equal to the probability of A. If those two things are not equal to each other, then you can consider the events dependent. Looking at an example of independent and dependent events, we are asked to decide whether the events are independent or dependent of one another. We will use the formula that we discussed on the previous slide to determine whether selecting a king from a standard deck, event A, not replacing it, and then selecting a queen from the deck B, event B, are independent of one another. So here's what we need to do. We need to determine what the probability of A is, right? What's the probability of event A? In other words, selecting a king from a standard deck. That's event A. So there are 4 kings in a standard deck of 52 cards, which if you simplify is 1 out of 13. 4 out of 52 is 1 out of 13. The probability of selecting a queen from the deck, probability of event B, is also 4 out of 52 because there are 4 queens in a standard deck. This also reduces to 1 out of 13. Now what we have to do is we have to determine the probability of selecting a queen, which is event B, given that A already occurred. So the probability of event B selecting a queen, given that a king was selected from the deck and not replaced, is 4 out of 51. Right? If I select a king from the deck and do not replace it, there's only 51 cards in the deck. Hence why I have 51 on bottom, the total number of outcomes, total number of cards left in the deck to choose from. The probability that I select a queen, because there's 4 queens in the deck, would be 4 out of 51. Now, I need to determine whether or not the events are independent or dependent of one another. In order for the events A and B to be independent of one another, the probability of B given A has to equal the probability of B. If you want to look back on the previous slide, we determined that the probability of B given A has to equal the probability of B in order for the events to be independent of one another. So I guess the question is, does the probability of B given A equal the probability of B? Are those two fractions equal to each other? If you divide 4 by 51, you get 0.078. 0.078. So 4 divided by 51, let me change my pen here, 0.078 needs to be equal to 1/13. And 1/13, if I divide 1 by 13, I'm going to draw up here at the top, 1 divided by 13 is 0.0769. So clearly, they're close. 4 divided by 51 and 1 divided by 13 are very close in value, but they're not equal to one another. Now, another way we could show that they're not equal to each other, if I erase this, if I want 4 divided by 51, if I want to know if that's equal to 1/13, we know that if two fractions are equal, their cross products are equal to one another. So 51 times 1 is 51. Does that equal 4 times 13? So if I multiply 4 times 13, I get 52. 51 clearly is not equal to 52, therefore the fractions are not equal to each other. And since the fractions are not equal to each other, since the probability of B given A is not equal to the probability of B, we say that the events selecting a king from a standard deck and not replacing it, and then selecting a queen from the deck, event B, are dependent events. All right, we're going to talk a little more about independent and dependent events. We have another example here. Instead of using cards this time, we're asked to toss a coin and get a head, and then rolling a die and obtaining a 6. So we have two different events here. Event A is tossing a coin and getting a head. Event B is rolling a die, a 6-sided die, and obtaining a 6. Are the events independent or dependent of one another? Here's what we'll do. Let's look at each individual event separately first. The probability of A, tossing a coin and getting a head, we should know is 1 out of 2. We have a 1 out of 2 chance of getting a head when flipping a standard coin with heads on one side and tails on another. The probability of event B, rolling a die and obtaining a 6, is 1 out of 6. What we need to determine is the probability of B given A. What is the probability of event B? In other words, what is the probability of rolling a 6 on a die given that I've already flipped a coin, event A, and landed on heads? So the probability of rolling a die and getting a 6 is not affected by the fact that I already flipped a coin and got a heads, So the probability of rolling a die and getting a 6, given that I've already flipped a coin and got a heads, is 1 out of 6. Now, to determine whether events A and B are independent of one another, I need to show that the probability of B given A, this, is equal to the probability of event B. Well, the probability of event B was 1/6, and the probability of B given A is also 1/6. Therefore, since the probabilities are equal to each other, we can say that the two events, event A, tossing a coin and getting a head, is independent of rolling a die, 6-sided die, and obtaining a 6.